Good morning, and let's see. I see I'm getting something there. Let's try this. So what? Well, welcome to Equisingularity. This is the fourth lecture in the course on ICIS. Oh, that's interesting. So these next remarks are addressed to the students. I encourage you all to read the notes for lecture 4. They should be online very soon. And they will also be used in the course on determinantal singularities next week. Yes? They are already online. Wonderful news. So the notes have a number of exercises. Try to do as many of the exercises you can. And this is something that I encourage everybody to do when you are learning a new subject. Whenever you hit a definition, make up an example, an easy example that you can solve in order to understand the definition. And we will have an exercise session next week. Also, I'm going to try to make myself available to people. I'm a little bit busy now working on talks, but I really would like to talk to everybody who wants to talk to me. If you have a question about the course, please feel free to interrupt me whatever I'm doing and talk to me, because you have the highest priority. Okay, so here we have an introduction to the subject and some basic examples. So to understand a singularity, as Sudina said yesterday, we want to understand the nearby singularities, the singularities that appear in deformations of X. And we can also ask the same thing about families of maps. Given a family of maps, one of the maps all the same, one of the members different, and equisingularity is the study of these questions. The big advantage is that when you have the sets all grouped together, it's easy to see which one is sticking out. And when you have two individual sets over here, it's hard to compare them. So often when you have a family, the change in a single invariant suffices to pick out the different members of the family. Another advantage to working with families is that if we have a family, we can take derivatives. And so we can use infinitesimal methods to study the family, and that's one of the goals in this lecture. In the ISIS case, we have the wonderful happy coincidence that the invariants we look at have both a topological geometric interpretation and they have an infinitesimal interpretation. An example, case in point, is the Milner number. Whoops, how about that? Let's try this. There we go. So the Milner number is both an infinitesimal invariant, that is the extended RE group tangent space codimension, and it's the rank of the middle homology of the Milner fiber, and that's the geometric interpretation. And that is what we're going to be, the kind of thing we're going to be looking for. So first we have some notation. I'm going to be looking at families of sets. This is the total space of the family. Y is always going to be the parameter. And this is important. We always assume that the total space is equidimensional and has equidimensional fibers. And we usually assume that the parameter space sits inside the total space of the family. And we have some notation for the defining equations. Capital F will be the one that defines the family. And if we take capital F and specialize fixing Y, we get the fibers. So we assume that this defines this, and we assume that this defines this. Okay. Thank you. So Sx is the singular locus of X. Thank you for paying attention. Pardon me? What in the diagram? Oh, in the diagram, capital S, well, this is a generic notation here. So if I'm talking about x of y, capital S is in x of y. Whoops. Capital S is in x of y if x is x of y, and capital S of x is contained in this family if x is the family. So here we have some definitions and examples. We say that a family is smoothly trivial if we can trivialize it with holomorphic germs, by holomorphic germs. If the trivializing family is only homeomorphisms, we say it's C0 trivial. So here we come to our first example. X is a family of two moving lines in the plane with this equation. And so we have this picture. Notice that one of our lines is fixed and the other line is moving. So this is where we are when y is 0. And when we advance a little bit, if we advance y, whoops, let's take this out. We have a picture like this. Is this family equisingular? Well, the answer is yes. Our intuition says they should be the same, and in fact, they are, because we look at the functions that define the family, the individual members, and we see that these are all going to be equivalent to this guy because these are all Morse functions. Great, families of two lines, they're equisingular. Problem, show that the family of three lines, where one of the lines is moving, is analytically trivial as well. And now we come to four moving lines. So, should four moving lines give us an equisingular family? Yes. But unfortunately, here's a picture of our four moving lines. You can see that three of the lines are fixed. Z1 and Z2 are fixed. And this is the, there's another line here. And this line here is fixed too. So these are the three fixed lines. And you can see that's why they're not moving. They're just planes. And this is actually a surface in the family, the whole space of the family. And that is made up of the moving lines. Well, problem, show that these are not smoothly trivial. And I have a hint. So the idea is that if you did have a trivialization, it puts too much pressure on the poor derivative. The derivative has to fix three lines, and if it fixes three lines, it can only be a multiple of the identity, and then it has no way to fix the fourth moving line. So these are not smoothly trivial, but we still want to use infinitesimal methods as the foundation of our theory of equisingularity, because using vector fields will allow us to use basically the same tools, same things that Mather used in his work on smooth equivalence. So if we can't use smooth vector fields, because smooth vector fields would integrate to give us analytic trivializations, we can't use smooth vector fields. What kind of vector fields do we use? So now I want to talk about Rigaud's vector fields and Verdier's condition W. Okay, so if we have a family of hypersurfaces, we're going to work in the hypersurface case first. And then we're going to define a vector field. Wow. Okay, so notice that this vector field along the y-axis is just the partial with respect to y. That will ensure that the flow we get moves us from family member to family member. Now this looks like a mess, Well, let's see what we got. Down here we have the norm of the partials of f with respect to the z variables. Here we have the partial of f with respect to y. That's in every single term. And then here we have the complex conjugate of the partial of f with respect to z, I. All right, what happens? Well, first off, v is well defined whenever the derivative with respect to z is not 0. And furthermore, if we apply this vector field to f, we see that it's 0 where defined. And so the key thing is v must therefore be tangent to x0. So if we could integrate v, the family of homeomorphisms we get would trivialize the family. So we want to make sure that that c of y0 is 0. So this has to preserve the origin. And we want the flow of v to be at least c0. And now this brings up the notion of Ragow's vector fields, which was due to Verdier. And Verdier showed, using some analysis, that provided you had a condition on C, then you would get an integrable vector field. So what is Verdier's condition? So the C part has to go to 0 at least as fast as the distance to the y-axis. That's what we need. And Verdier called such a vector field a Ragow's vector field. And Verdier also defined a stratification condition. The stratification condition guaranteed that if you had a vector field on a lower dimensional strata that was Ragow's, you could lift it to the higher dimensional strata. So I want to talk about what condition W is. And the first thing we have to do is talk about the distance between linear spaces. So suppose A and B are linear spaces at the origin of Cn. All right, so what's the distance between two linear spaces going to be? So what do I want to do? I have B is going to be the big space. And I'm looking at vectors which are perpendicular to B, different from 0. A is the small space, and V is just a vector in A. Then I look at this is basically giving me the angle between U and V, as we'll see in an example. Here's our example. A is the small space, it's the x-axis. B is a plane with unit normal, U0. Then what happens here? Well, this is 1, this is 1. So we just get U0 dot the tangent vector to A, that's the tangent vector to A, and this is just cosine theta, where theta is a small angle between U0 and the x-axis. So when the distance is 0, theta is 0, and U is perpendicular to A, and so B contains the x-axis. Because anything perpendicular to U is in B. So now we can define Verdier's condition W. Key points. The distance between the tangent space to the small stratum and the tangent spaces to the larger stratum have to be less than or equal to the distance from the point here to y. If this happens for all x close to y, then we say the pair xy satisfies Verdier's condition W at 0. Verdier did this in 76. Theorem, also proved by Verdier. The points where x0, y satisfy W is the Zariski open and dense. So at most points, we have this condition holding. We just have some Zariski closed set where it might fail. So now we can define what we mean by a W equisingular family. So the family is W equisingular or just plain old equisingular, because we aren't considering any other equisingularity conditions today. If we have a stratification in which every adjacent pair satisfies condition W, and we needed the parameter space Y is a stratum. Example, whoops. If we have not just 4, but n distinct moving lines in the plane, then this is going to be W equisingular. Why? Well, the idea is that X is made up of n smooth surfaces. We saw that in the picture for 4 lines. We saw there were 4 intersecting surfaces that intersected on Y. Okay, and whoops, now I've done it. Oh dear. Wow. So the idea is that each component of X0, each smooth submanifold satisfies W over Y, so it holds for the union of the components. Okay, so Tessier showed that Verdier's condition W was equivalent to the Whitney conditions that had been defined previously by Whitney, and at least when you're working over C. So whenever you hear Whitney in any of the talks that we're giving in the conference and you're working over C, you can just think W. And you can get a feeling for what those stratifications might be like. Well, W has an analytic inequality. So we want to use the basic setup with X, a family of hypersurfaces, and YK cross Cn plus 1. We know that the theorem is that condition W holds provided that the partial of F with respect to Y is less than or equal to the sup of the partial of F with respect to Zj, Ci, for all Yz in some neighborhood U at the origin. So what we want to do is we want to take the definition of distance that we started with, and we need to recast it in terms of the defining equations. That's what we're going to do. Okay. So here's the proof. For simplicity, I'm just doing one, well, I guess I'm doing more than one parameter. Set A equal to Y. Calculate the distance between Y and a tangent plane to X0. So for U, we're going to use, we just have one normal. I've made it orthogonal here, or I've normalized it here. And then we use the standard basis vectors for A. The distance formula says that W holds if and only if, let's go back. All right, so when you plug in, this is what you get. The partial of F with respect to Yi divided by the derivative with respect to F is less than or equal to C times the C double prime times the distance of the point. We're looking at the point here, we're looking at its distance to Y. And that we know is less than another constant times the sup of the Zi. Okay, so this is also equivalent to getting your hands, well, we're going to bring the denominator, take the denominator and put it right there. There it is. And it's also equivalent to the sup of this and the sup of that. And that gives the result we want. So we want to denote the ideal of the partial derivatives with respect to the z variables by Jz, and the ideal generated by the coordinates by m sub y. It's a sub y because the z's are defining y. When the z's are 0, we're on y. So this is a set of generators for for this ideal my times jz of f. And we ask the question, the inequality says that the partial derivatives of f with respect to y go to 0 as fast as the ideal does. Because we see that the partials with respect to y are bounded by these generators. Oops. We had one more question to go, Okay, so anyhow, we want to ask, how do we know when an element goes to zero as fast as an ideal goes to zero? And this brings us to the theory of integral closure of ideals and modules. So this is what we're trying to describe. We want to do it algebraically. Well, so we have this notion of integral dependence, which has both a analytic side and it has a algebraic side. So we have some equivalent conditions. Okay, the first one, if you're familiar with the notion of integral dependence for functions in a ring, it's very similar. We have this, we're going to have a polynomial, and here I've evaluated the polynomial at f already, so this is f to the k. And then we have coefficients, where the coefficients are in powers of I. And if I take the power, this is, for example, a1 is contained in I. So a1 times fk minus 1 is also contained in ik. Well, it's not contained in ik, but the things sum to k anyway. All right, the second one is the analytic condition. This is what we want. This says that an element, whoops, this says that an element is less than or equal to the generators of an ideal times the constant, if and only if it's contained in the integral closure of the ideal these generate. And then the third condition is one that is very useful in calculations and often interesting theoretically, and we'll look at this one. The pullback of f by a curve phi, so that's f composed of phi, that must be contained in the ideal, in the pullback of the ideal generated by I in the local ring of C at 0. And if it turns out that when I pull f back, it's actually contained in m1 phi star of I, then we say f is strictly dependent on I, and we write f is contained in I dagger. And that's a very useful notion exploring some of the stratification conditions. Okay. So all the elements that are integrally dependent on I, that's called the integral closure, and it's denoted I bar. And the first thing we want to prove is that if I is an ideal, then I bar is an ideal. So we use property 3. Here, phi is any analytic curve, and G is an element of our base ring. F1 and F2 are an I bar. All right, so we want to show that this is contained in I bar. So we compose it with phi. Notice the composition is linear here. And we know that this is in phi star of I, and this is in phi star of I. So this phi star of I is an ideal, so this whole thing is in phi star of I, and we've checked it. Here's another example. Supposing we have the ideal that is generated by x to the n and y to the n. And supposing we have any monomial where I plus j is greater than or equal to n. So now I'm going to write down a monic polynomial, which for this f is going to be 0. So we just look at t to the n, x to the n times I, y to the n times j, using these exponents. Now where is this? Well, this is contained in ij, and so it's contained in I plus j. We notice that if we take xi, yj and raise it to the nth power, it agrees with this, and so this is 0. So that says that f is an I bar, and I bar contains a power of the maximal ideal given by n. Great. So now we come to the first proposition, first theorem. We have a condition for W to hold in terms of this theory of integral closure. We have that W holds for this pair at 0 if and only if this partial derivative, all these partials with respect to y are contained in in the integral closure of the ideal that defines y times jz of f. And the proof is very simple. We know that W holds if and only if this condition holds. And by property 2, the analytic inequality property, we know that that implies that we get the result that we want. So that was pretty simple. And here's a problem you can try. Use directly from this inequality here, try to show that, or at least, try to show using these integral closure methods that the family that this function here defines, where h is anything in M2 n plus 1 is W equisingular. And I suggest that you try to use the curve criterion to prove that the, whoops, now I've done it. You want to use the curve criterion to prove that the partial with respect to t, which is h, is contained in jz of f, mjz of f bar. Try to do that. And then once you do that, then you use this proposition here to get the result. Okay. Well, what about higher codimension sets? What about higher codimension sets? So now we want to move into the theory of the integral closure for modules. We need some motivation because this is a non-trivial step. Verdier's condition, yes, question? I'm sorry, could you speak up? No, but the notion of integral dependence does have strong links to the notion of normalization. It does. And there's a discussion of that in the notes if you want to read that. That's a useful point. I think actually the theory of normalization was probably what moves Zariski to actually define the integral closure of an ideal, though he doesn't say so explicitly. But if you look at the back of Zariski's Samuel in the appendices, Zariski knew what the integral closure of an ideal was. There's no doubt about that. In fact, he probably knew what the integral closures of modules was. Okay. Anyhow, here we're working with tangent spaces, but if we look at the distance formula more carefully, we see that this u, if it's any vector perpendicular to x, this u will define a hyperplane. If we look at all vectors that are perpendicular to this particular u, we will get a hyperplane out. So we can rethink the distance formula. And in fact, this will be a hyperplane, which is a tangent hyperplane. And we want to use the notation that these are going to be c of x for the conormal. It's the fiber of the conormal of x over x. And then the distance formula becomes the distance of the tangent plane to the distance of t to the tangent plane of x is the sup of the distances of t to h of x, where h of x is now a hyperplane. Okay, hyperplanes. Well, just as an example, not as an example, if we look at maps to CP now, okay, so now I'm looking at maps. So these are the coordinates of my map. At a smooth point of x, if I take any one of these and take its derivative, that defines a linear form. And that linear form is a hyperplane, and it must be a tangent hyperplane because it must contain the tangent space to x. All tangent vectors to x are killed by this guy. So the projectivization of the row space of the matrix of partial derivatives is the conormal space at a smooth point. And this suggests looking at the module of partial derivatives, because the rows of the Jacobian matrix are just going to give us a basis for the tangent hyperplanes. Well, what does the integral closure of a module mean? Well, let's look. We need a little bit more notation. So we have M contained in N contained in a free module. And I want to assume that M is generated by G generators. And this notation means the matrix of generators. Then the way we get into the game is to use that curve criterion. So we're going to look at all curves. We take our vector, our p-tuple, and we compose it with phi, and we ask that it's in phi star of M. And the integral closure of M, denoted M bar, consists of all H integrally dependent on M. Great. Well, what can we do with it? Problem, show that M is a module, and show that M bar is M bar. How will we prove that M is a module, folks? How will we prove that M bar is a module? Sorry, I missaid it. How do we prove that M bar is a module? How will the proof go? Isn't it the same as the proof for ideals? Yes, it is. Right. Same as the proof for ideals. So here's an example. And I don't have time to talk about the example, unfortunately. I do want to talk about the module analog of property 2 for ideals. Okay. So not surprisingly, given our preliminary discussion, we are going to be judging the size of things. Here, the phis are contained in HOM CPC, and the generators are these SIs. In matrix terms, what's going on is that we're looking, this is a row vector. C dot SI is a row vector. And we're comparing this row vector with the corresponding combinations from the H's. And we need that to be hold on a neighborhood. Row vectors of M with a corresponding element of H. Important point, C and U depend on H and M, but they don't depend on psi. They're independent of psi. Now this means, since they're independent of psi, and it holds on a single neighborhood for all psi, we can replace psi with just a constant vector, and we will get the same result. This takes a little bit of thought, but it's not too bad. Let's see. So if we start here, then we can replace psi by t, and we have a statement that must be true. This is the case where psi is just constant. And conversely, let's see here. So, whoops, we went too far. Oh, here's the converse here. Oops. I apologize for my clumsiness with this thing. Right. Any S, no. Yeah, here we go. So conversely, we can replace, right? We can replace T by phi. So this is a constant. How can I replace it by phi? I can use the fact that the value of phi at every point is just another constant. The value of phi is just a different t. And the constant c is independent of the choice of t. Doesn't matter which value it takes. So that's that. Now, the reason for this lemma was because I wanted to get to the main result of this first part of the talk. Namely, if we have the partial of f with respect to y as containing the integral closure of my jmf, then we have w. So we get a result which is completely analogous to the one that worked for hypersurfaces. But this holds in general for all spaces which are families of equidimensional sets. Okay, so what is the idea? So what we're going to do is we're going to rework the form of Verdier's condition W to fit our current framework. At a smooth point of x, a conormal, a vector can always be written as S, some constant, times df of x, where S is in CP. S may be different, but it's unless this has rank P. Conversely, any such S gives a conormal vector. And it also clears that W holds if the distance inequality holds for the standard basis of the tangent space of Y. Then this is our distance formula, and it becomes, well, let's see. U, the norm of U is this guy here. That's what's appearing in the bottom. Here's the norm of U, and here it is again. This term here is the V dot U term. So this has to be less than some constant times the distance. And now I've just brought the denominator over to here. So this is what it becomes. So this is Verdier's W. Now we look at the integral closure condition. And then we have some more stuff. This is the integral closure condition. Using the last corollary, we have that this is contained in the integral closure here, if and only if any S times this is less than or equal to this. And you can see clearly that it's the same, and that finishes the proof off. Okay, so I have one last little thing to do. This is a sort of a technical thing, but it's important. This is the Jacobian module of F. This is something that lives on the total space. This is the partials with respect to Z. Now, what do I get if I take, let's do it, writing it out here. What is this module, which lives in the total space, turned into when you restrict it to x of y? It is it's just the Jacobian module of xy. I want theorems that are about what happens fiber by fiber. So I have to take this guy, which is something on the total space, and replace it by something, oh dear, and replace it by something which is something which lives only, which does have a good restriction when I restrict to a fiber. Okay, so what are we trying to do here? So there's our notation. And what we want to do is show that we can forget about Jm of f. We want to show that we can replace Jm of f by Jmz of f if we're only doing things for W. So it's clear that Jmf y contained in here implies that Jmfy is contained in here. This is the big thing, this is the small thing. If it's in the small thing, it's got to be in the big thing. So take a curve. All right, let's see what we get. I'm looking at phi star of Jmz. I know it sits inside phi star of Jm of f. It's a submodule. This is equal to phi star Jm of z by definition, and the parts with respect to y. Aha. This part here is actually contained in M1 times phi star of JMF. So how do I conclude that this is equal to this? By what famous theorem? Nakayama's lemma. Excellent. Okay. So by Nakayama's lemma, they are the same, and the same thing works here. Oops. And since phi is arbitrary, we're done. So for W, we compare the size of the row vectors of d of x with a part of the row vector from dy. Since the part coming from dy must go to 0 faster, it's sensible to compare it with the part coming from dz. And the last proposition justifies this intuition. Okay, so here's where the payoff comes. Oops, damn. Now we've jumped too far ahead. Okay, so what the payoff is this. Given a family of ices, this thing does restrict to the Jacobian module of x. If it's an isis, it has finite colength in here. So that means the multiplicity of this module is defined. In the next talk this afternoon, we'll see how the multiplicity can be used to give necessary and sufficient conditions for W to hold for a family of ices. Any questions? Yes. Please wait for the microphone. It's coming.
So I was wondering, you talk about the integral closure. I was wondering if there is some estimation for what should or should not be contained in the integral closure of, say, a module or an ideal.
I'm sorry, I have a hard time hearing.
So if we have an ideal,
We have an ideal.
or a module, we take the integral closure.
Yes.
Is there any estimation of what should be or what shouldn't be?
Oh, so how do you figure out what should be in the integral closure?
Yes, that's a question.
Right. So during the exercise section next week, I'm going to give lots of examples of how you can compute the integral closure of an ideal. Just as a preliminary, suppose this is the Newton diagram and F is Newton non-degenerate. I have to say what that is, which I'll do Monday. Non-degenerate. Then this is J of F bar. Okay. This is a much better result than you can get if you're trying to calculate what JF actually is, in terms of simplicity. Okay, any other questions? Okay, great. Well, this is a lot to digest, and as I said, I hope you think about it. We have a couple hours for the afternoon talk. Feel free to ask me if you have any questions about.
Terry, I'm sorry.
Oh, yes.
I just want that you remind us if in the main result about the integral closure condition for the equivalence with the W condition, if you are looking at the Jacobian model
Yes.
as a submodel of O and P or a submodel of OX.
Yes, so we're looking in the main result. We're thinking about this would not have finite colength unless, well, actually, in this case, it does. In general, this doesn't have finite colength unless you look at it inside the OX module it came from. So, Okay. Very good. Thank you.
the time I finish my introduction, they'll start it. So I was told to keep things very elementary. So with the risk of boring some of you, I will get back to the basics. Topology 101. You will see something quite different from the previous lecture, very topological. And I will try to attack some exercises I left in the file I posted, I discussed on Tuesday. I hope in the meantime, some of you had a chance to look at some of the video recordings. If not, if you're interested in the subject, please do so at some point. All right, so I was talking about projective hypersurfaces. I don't know if you can see this. Can you see this? Should be able to see it on the screens at least. All right, so let me recap some notation. So V was F is equal 0 in CPn plus 1, where F is a homogeneous degree D polynomial. And for future reference, let me just take, let's say it's reduced. Let's say V is reduced. V or F are reduced. So this means that F has a square-free reducible decomposition. So square-free, and each of these Fi's are irreducible. And I'm going to denote by V sub I the irreducible components of V. Say maybe DI is the degree of Fi. Okay, so these are just notations. So now what I want to do, remember my goal was to try to understand something about the topology of such a hypersurface, in the sense that I want to understand maybe Betti numbers or even integral cohomology. And today I will try to say something in that direction, but as elementary as possible. So I'll start with the top cohomology. So as a complex, well, as a topological space, this V has real dimension 2n. So, or as a CW complex, its homologies, cohomology are concentrated between 0 and 2D. And let's look at the top one, let's say with Z coefficients. From the long exact sequence of the pair between V and the singular locus, this is the same as the relative cohomology of V rel sing V. Sing V has dimension, real dimension at most 2n minus 2. So in the long exact sequence, you get this isomorphism. Then by duality, I call it Alexander duality. Some people call it Alexander-Lefschetz, others just Poincaré. It doesn't really matter. This is just H0 of the complement. And that is what? So if I have, for example, curves, of course, you may have singular things also, but they all intersect at points. And once you take out the singular locus, what's left is just a bunch of connected components, one for each irreducible component of V, and those will count this H0. So this is just Z to R, R being the number of irreducible components. So the top cohomology is just Z to a number of irreducible components. This we saw already on the slides, but I did not explain this. So I should say that, again, the complement has R path components, one for each irreducible component of V. All right, so this is an easy calculation. And now let's try to make use of the embedding of the hypersurface in the projective space. So feel free to ask questions if something is not clear. And also feel free to stop me when I'm done, when my time is up. All right, so now let J be the inclusion of V into the ambient projective space. And these results I mentioned, Lefschetz and Kato theorems, have to do with how this map behaves in cohomology in some range. So now let's first look at the top piece. So this would be something that Kato's theorem addressed already. So if I look at J in degree 2n, in cohomology, let's say, yeah, still with Z coefficients. What is this? This is just take, so of course this is just Z, right? So take an integer, and what this maps to is, now this is Z to R. Well, I should get R integers there. So what are they? Well, D1 times A, D2 times A, and so on. Where the di's are just the degrees of the irreducible components of V. So this is just a reflection of the fact that each of these VI's in homology are given by their degrees times the hyperplane class, or put differently, a generic line intersects each VI at DI points. All right. Now, I have a little lemma here. Yeah, I should say that most of these things are, of course, in books. This is nothing really new here. So the lemma I have here is that the odd Betti numbers of V are at least 1 for any hypersurface. Sorry, not the odd, the even. Even, odd are the same thing, but if you add 1, right? All right, so what is really meant here? In fact, what happens is that this cohomology maps, let's say JK, from the kth cohomology of CPM plus 1, C, let me use a field now, of course. For Betti numbers, I don't care about anything else. This injects into the cohomology of V. So now this is for all K. From 0 and to n. So in all degrees. Of course, in odd degrees, there is nothing really to prove because the left-hand side is 0, but otherwise, this really tells us that the corresponding Betti numbers of V have at least as much as those coming from the projective space. So this is, again, very easy because, I should try to remind the students that as the cohomology, maybe I should not write it like this. So the cohomology ring of the projective space is generated by an element of degree 2, so alpha is generator of H2 of CPM plus 1. And let's say from now on I'm going to use this notation. Alpha V is the pullback. So J2 means whatever J does in degree 2 of alpha. So this is an H2 of V with C coefficients. This map is a ring map, ring homomorphism. So all I have to show is that alpha V, well, to all powers up to n is not trivial, but for this it's enough to show that the top power is not 0. So when I say power, I mean power with respect to cup product. So I just take this degree 2 cohomology class, copy it itself n times. All right, so this is again, I mean, it's very easy because this really corresponds to, maybe let's write it down. So I'm going to use the Kronecker pairing here. So I take this cohomology class, alpha V to nth power. I evaluate it, let's say, against VI being the homology, the orientation class of the irreducible component VI. So this is just J2n of alpha to n, and using the usual projection formulas, what you get here is just alpha n and then J push forward VI. I'm doing some basic calculations from topology 101. Now what I said here is that this guy is just di times the hyperplane class. And alpha itself corresponds to the dual of the hyperplane class. So what you get in the end is just di. So this alpha n really corresponds, alpha v to n in cohomology corresponds to what I said earlier, d1 up to dn, d1 up to dr in Z2R. All right, so this is something to keep in mind. It's a very useful piece of information because now I can do something no one else has done before. Namely, move this board to the left, to the right. Can I do that? I will clean it after that. I just hid. I didn't see anyone doing this. I just discovered it's possible. All right, so a quick corollary of this lemma is that the long exact sequences in cohomology for the pair CPM plus 1V break into short exact sequences. Well, I'm not saying anything out of ordinary here. So HK of CPM plus 1, C. Then I have this map JK to HK of V, C, and then the pair. All right, we'll see in a minute what this is good for. Why I started with this. So now let's recap a little bit what Kato's theorem said. And I want to move a little bit to the exercises I left on the slides. So recall Kato. So Kato said that if S is a dimension of the singular locus of V, then this map JK is multiplication by D. So D was the degree of V for K between N plus S plus 2. Okay, I should not write here. So K between N plus S plus 2 and 2N. Okay, so for this statement to actually be meaningful, I should make a quick remark. This wants N to be at least S plus 2, so singularity should appear in codimension at least 2. Least or most, I don't know how to say it. There are no codimension 1 singularities. So this says that for this statement to be meaningful, V has to be reducible. Otherwise, it doesn't give us anything new. Of course, I cannot. So again, JK is this map that I wrote here. All right. So I put a corollary on the slides, or an exercise, which said, well, if V has the same cohomology algebra as CPN, then, and N is at least 2, then V is CPN, or isomorphic to CPN as varieties. So this was an instance where topology, or at least the cohomology algebra, tells us the algebraic structure, and this is something which I tend to like very much. Before I justify, this was an exercise on the slides. Before I justify this, let me make a few remarks. So first, we saw that this assumption N at least 2 was necessary because if you work with curves, like cuspidal curve, for example, that's homeomorphic to CP1, but it's not CP1, of course. Another remark is that there exists V with isolated singularities and same homology as CPN. But of course, since V has isolated singularities, cannot be isomorphic to CPN. The catch is that here I'm only asking for the same homology, which is much weaker than the cohomology algebra. And in fact, all these examples are topological manifolds. So this means the links of their singularities are topological spheres, but they're not diffeomorphic to spheres. All right. So this is the difference between algebra versus just groups. So why is this really on the nose? Why is this so easy? I have to say, no one should really feel bad if you don't see the argument right away. I normally would say a sad story about this, but maybe I should refrain now. So people in, higher power than students have difficulties seeing this, so including myself at first time. All right, so what's behind this? What is this story with V has the same cohomology algebra as CPN. CPN is generated in degree 2. It's cohomology algebra. CPN is irreducible. Well, just by looking at the top cohomology and the previous thing I just erased, it should tell you that V is irreducible. So assumptions of corollaries, of the corollary, imply a bunch of things. V is irreducible. The other thing is that H2 of V, yeah, sorry, here I should say Z algebra, of course not. This is even more powerful than it looks. So H2 of Z is generated by alpha V is J2, so pull back under the inclusion of the generator of CPN. So this tells us now that since I have the same Z cohomology as CPN, this says that the powers of this alpha V generate the even cohomologies of V. So in particular, alpha V to N generates H2N of V, which we now know is Z, right? All right, so now so far I didn't use anything except V having the same Z cohomology algebra as CPN. Now what I want to do is to use Kato. So Kato says, so V is irreducible, so I can actually use Kato at least at the top level. And Kato says J2N is multiplication by D, by the degree. So Kato implies J2N from H2N of CPN plus 1, which is the same as CPN, of course, to H2N of V, is multiplication by D. Okay, so I don't know how to write this, but all right, so what I get here, on the one hand, is alpha V to N, which generates H to N, should be D times something, the generator coming from the left-hand side. So D times some generator. Generator gets mapped to generator. Sorry. Generator gets mapped to D times the generator. That's what Kato said. On the other hand, I already know what the generator is. It should be this guy. So now, this is the generator of Z. This is a generator of Z. And they should differ by multiple of D. Of course, that's not possible unless, so I should say here, generator of Z. Not possible unless D is 1. So D is 1 means the defining polynomial is linear, hence V is a hypersurface, is a hyperplane. Okay, so this was one of the exercises I left on the slides. So now I want to actually get to some examples. Questions? Yep. Is what? Is given by? By T? Yeah, it's given by the inclusion, yes. Yeah. Yeah, this is what this means here. So J has the same Z cohomology algebra under this inclusion J. Yeah. That's why we get these conditions here. All right. So now, what I want to do is using, I'm going to erase this. And I get back to the Betty numbers. So I gave you some conditions under which topology determines the algebraic structure. So having the same Z cohomology, but of course this is very powerful, right? What if I just have the same? What would guarantee, for example, that I have the same Betty numbers just? Forget about Z cohomology is very powerful. So here is a little thing. So BK of V equals BK, so these are Betty numbers, of CPN or CPN plus 1. If and only if, well, this JK is an isomorphism. And that will tell me the third term of the sequence has to be 0. Okay, now by Alexander duality, this is nothing but H. I never remember this, 2n minus k plus 1, I think. So the sum should be 2n plus 2 of the complement, of the affine complement. So our hypersurface is the same Betty numbers as the projective space, so just zeros and ones, if and only if the homology of the complement is trivial in all degrees. Now, recall that we had, so if F, capital F, is the Milnor fiber of F at the origin, so F now regarded as a polynomial on Cm plus 2, it's homogeneous at origin. Then we said that F provides a D to 1 covering map to the complement. So the homology of the complement is really, this is really, so this guy is really F mod the group divided by the homeomorphism, the monodromy homeomorphism. So H is the monodromy. Is multiplication by roots of unity of order D, by a primitive root of unity of order D, because F is homogeneous. So the homology of the complement is going to be just the invariant part of the homology of F under the monodromy homeomorphism. So this is just homology in the whatever degree of F invariant under H. Okay, so V has the same Betty numbers as the projective space if and only if the invariant part of the Milnor monodromy is trivial. So this means if and only if the Milnor monodromy doesn't have the eigenvalue 1. That's all. And this was a statement I put on the slide in the lectures on Tuesday. So I don't know, I should write it like this. This is the typical example of bad teaching. So this is an equivalence. H doesn't have eigenvalue 1. on the homology of the Milnor fiber. All right, so now I can do examples. And now we can actually get a lot of mileage by essentially cheating, by using calculations of monodromy. All right, so here's an example. How much time do I have? Till 10:10 or something like this? Okay. Okay, here are the. So let's consider, let's say f of x0, xn plus 1. So these are the coordinates in Cn plus 2, right? Looks like g of x0, xn plus xn plus 1 to power d, where g is homogeneous of degree d, right? So f is homogeneous of degree d, but I split it like this. And assume the Milnor fiber of G assume, I don't know how to call this, HG or something. So the monodromy, this is the monodromy. So this is identity on FG, which is G is equal to 1. So G is a homogeneous polynomial of degree D in one less variables. It has its own Milnor fiber, which I call FG. It has its own monodromy, which I call HG. And let's assume that's identity on, well, I should say on the homology of this, of the Milnor fiber. So it's quite the opposite from what I want to have, that the monodromy doesn't have the eigenvalue 1 on the homology of the Milnor fiber. But now, for reasons that have to do with the local calculation of monodromy, you'll see some of that in Dirk's exercise session. He promised he will solve all my exercises. Will you? I hope so. All right, so Tom Sebastiani. Tom Sebastiani gives us a way of computing Milnor monodromy for polynomials which can be split like this into a sum of polynomials of different sets of variables. So what you do, you calculate the Milnor monodromies for each of these summands, and then there is a way of concatenating them. So the Milnor fiber of the sum will be the topological join of the Milnor fibers of the summands, and the monodromy, the eigenvalues of the sum monodromy, are made of products of the eigenvalues coming from the summands, except the eigenvalue 1. So that doesn't count for anything in either of the summands. That has to do with the reduced homology of the Milnor fiber that comes up in calculations. All right, so now if I assume that G has its own monodromy trivial, and here I take all the eigenvalues of monodromy which are different from 1, by putting together, by concatenating this monodromy calculation, Tom Sebastiani will tell me that H star on the homology of the Milnor fiber of F doesn't have the eigenvalue 1. All right, so this seems still a bit abstract, right? So I'm in the situation of what I came up with here. So this in particular will tell me that V defined by F has same Betti numbers as CPN. But this is still a bit abstract, so let me give you a more concrete example here, or two examples, and I'll end with this. So first, this I put already on the slides. Take x1, x2, and so on, xn. No, sorry, from x0, x1, xn. So now this is a polynomial in the variables up to xn of degree n plus 1. Add to it xn plus 1 to the degree. And the claim is that this has the same C homology or same Betti numbers as CPN. Well, so this is our G. And as you will see, maybe in some special cases, the monodromy, Milnor monodromy of this polynomial is trivial. It should be a classical thing, but I don't want to spend another 10 minutes discussing this. So HG, so the monodromy of G is the identity on the Milnor fiber of G. So I don't know, if you just work with, let's say, n is equal to 1, this is the classical nodal thing, which by a change of coordinates is just the sum of squares. And again, Tom Sebastiani will say, well, how do I calculate the eigenvalues of the monodromy of this guy? I take the eigenvalues here, which are not 1. In this case, it's just -1. Take the eigenvalues here, which are not 1. In this case, again, -1. Multiply them, you get 1. So you get what I said. The monodromy is the identity. You can use polar coordinates and all of that to do it in the general case or work by induction. But this is a good example to keep in mind. So I said that this is just about the same C homology, not about Z homology. So for example, H, what did I say there? H3 of V2. So n is 2 with Z coefficients has 3 torsion. Of course, you don't care about this for the Milnor numbers, but for the Betti numbers. But if you care about the integral cohomology, this comes up. All right, and the final example, which I will actually discuss, I'll reserve the last section, the last part of the presentation, just to discuss one example from various perspectives, running over calculations of Euler characteristics and so on. These are things that everyone should do at least once, even if you do differential equations. They come up with in the modules also. All right, so here's the example. So as I said, I'll discuss this in the afternoon. So this is x1 squared x2 plus x0 cubed plus x3 x0 squared plus x4 cubed. So this is not anymore, well, I mean, it is of this type, but maybe the monodromy. So this is our G here. Calculating the monodromy may be a bit more complicated because it needs to do some change of variables, but still it has separate pieces. So you can apply Tom Sebastiani on pieces, this one and this one. And the claim is that this has the same C homology as CP3. So calculating the monodromy of G and showing it is the identity, in this case, is not too difficult. But what I want to do eventually in the afternoon is to actually also discuss the following. In fact, this V is a Q homology manifold. So to do this, I have to discuss its Whitney stratification and local monodromies transversal to strata. And then to do the, so Q homology manifold will tell me that the Betty numbers I have below middle, which are given by Lefschetz, replicate above the middle. So the only thing that was left to calculate is the middle Betty number, which is B3. So B3 will be 4 minus the Euler characteristic. So B0 is 1, B1 is 0, B2 is 1. These things replicate above the middle and give me this 4. And I have B3, right? So this is the formula between the Euler characteristic and B3. How do we calculate the Euler characteristic? This is a formula that I put on the board last time. This is the Paroshinsky-Pragash formula. We'll do this specifically using a stratification. And once we do this, we'll find B3. B3 will be 0. So the Euler characteristic will be 4. So we'll do this in the afternoon. Along the way, I'll have to calculate the Miller monodromies of the Miller fibrations in the transversal direction to the Whitney stratifications of Whitney strata of V. And for that, again, you'll see perhaps more in the problem sessions of Dirk. All right, I'll stop here.
So there is still some time for questions or comments. Okay. So now it's time to take our official picture. Let's meet in front of the building. Okay.